Now that we've talked about why we are interested in an LU factorization, it's time to talk about how to do an LU factorization. So let's suppose that A can be reduced to an echelon form U by using row replacements that add a multiple of one row to another below it. Now what we're assuming here is that at no point do we need to swap two rows in the matrix. That is a condition that we are placing on this situation here in the beginning, and then later on we will remove that condition and allow for you to swap two rows. All right, so then there exists these elementary matrices, and recall that an elementary matrix is just a row operation that has been done on the identity matrix. So there's a series of elementary row operations that will reduce A to its reduced row echelon form. So if I just took all of the row operations that were required to reduce A to U, and then did each one of those row operations on the identity, that would give me a list of elementary row operations. And then since since the row operations are done from right to left, I would put the first row operation on the left side of A, and then the second row operation and the third row operation up to the last row operation. And that all of those would reduce A to the echelon form U, which this U is going to be the U that we have in our LU factorization. So since all row operations are invertible, all elementary matrices are invertible. So if I have this equation here, I can multiply both sides by the inverse of the elementary matrices to end up with this equation, and it will turn out that the inverse of all of these elementary matrices will be lower triangular, and so that is going to be my factorization L times U. All right, so it can be shown that the inverse of all elementary lower triangular matrices are lower triangular, and we will note that the row operations that reduce A to U will also reduce L to the identity matrix, since if I do all of these row operations on L, and I'm just noticing here that I have a typo, this should not be inverse. We had decided that L was the inverse of all of these row operations, so that's the way that it should look. So if I do all of these row operations, then I'm multiplying a matrix by its inverse, and that will give me the identity. Okay, so the algorithm is going to be that we will reduce A to its echelon form U by row replacements, and while we're doing that, we will place entries in L so that all of the row reduction will reduce L to the identity. Okay, so that's a lot of theory, and it could be a little bit confusing, so let's take a look at an example. Here's my matrix A. You will notice that it is a 4 by 5 matrix, and I'm going to reduce this to LU, and L is always going to be square, so it will be 4 by 4, and U will be 4 by 5. Remember that U is a row echelon form of A, so U and A are going to have the same size. All right, we also know that L is going to have ones down the main diagonal and zeros above it, so it's about finding the entries that are going to be below that main diagonal. All right, so we begin by looking at the first element. So I'm going to take this 2, and I'm going to divide that 2 into all of the entries in the column below it. So 2 divided into -4, divided into 2, and divided into -6. Those results will end up being the first column of L. So when I do those divisions, I get that column of L. Now what I want to do is the row operations that would be required to take that 2 and use it to make zeros below that entry. So those row operations that would make zeros in the first column of A will also make zeros in the first column of L. Right, so what would those row operations be? I would need to do 2 times row 1 plus row 2, negative row 1 plus row 3, and 3 row 1 plus row 3. So I will do those row operations, and then we're going to repeat the process. Now I will take this entry, and I will divide it into the entries below it, and I will place those into the second column of L. Then I will do the row operations needed to make zeros below that entry, which would be 3 row 2 plus row 3 and negative 4 row 2 plus row 4. And then I'll do it again. Now I've moved down to my next entry, which is a 10. I divide that into the entry below it, which will give me negative 1. And now I've created my matrix L. Lastly, I will do the row operation to make that entry where the negative 10 is a 0. And once I do that, then this becomes my matrix U. So U is a row echelon form of A, and while I'm putting that into row echelon form, I am creating the matrix L. Now, the whole reason for doing this is to reduce computation, and when we're doing it with a 4x5 matrix, that may seem like that we did a whole lot of work to not get very much. But when you look at something like a matrix that has bigger than 30 rows and columns, an LU factorization takes about 2n cubed over 3 floating point operations, which is about the same as it does as it is required to reduce an augmented matrix to reduced row echelon form, whereas A inverse takes about 2 times n cubed. And what I want you to notice is that LU factorization takes about 1/3 the computation that is required to find A inverse. Solving the system of systems of equations takes about 2n squared computations. And again, in order to do something into row echelon form, it would take about 2n cubed over 3, so it takes a lot less computation. We saw that in the last video. Multiplication by A inverse requires about 2n squared flops, but the results may not be accurate due to round-off error. And then lastly, which also is very important, is that if A is sparse, where most of the entries are zeros, which in a lot of applications we have sparse matrices, then L and U will also have lots and lots of zeros, but A inverse will not.